Ever wonder how we take AI and cloud networking to its next frontier, solving both exponential growth and ironclad security? Today, we break down the multiplanar network architecture, a real game changer for large-scale AI and cloud infrastructure. Hello, welcome to First Principles, where we deep dive into OCI infrastructure engineering. Over the last few years, we've seen AI workloads grow not just in size, but also in complexity and criticality. Traditional networking is reaching scalability limits. Today, we will deep dive into multiplanar network, a transformative new network paradigm that takes network scale, performance, and reliability to the next level. Today, I'm joined by two of our network experts, Brar, VP and Distinguished Engineer, and David Becker, Network Architect, two of the masterminds behind OCI network architecture. Well, Jag and David, it feels like yesterday that we had this conversation about, the network architecture for, AI workloads. Well, you guys are in the trenches working on this. So what's driving the rapid innovation in networking?
The scale, customer demand is just out of this world. You hear news announcements all the time of new data centers.
Yep, customers, innovating their workloads, needing larger workloads, more reliable network, and more efficient networks.
All right, so let's set the stage here. Training large language models and generative AI models require massive clusters of GPUs or AI accelerators, sometimes spanning hundreds of thousands of GPUs. We launched Zetascale Cluster Network last year that can span to more than 130,000 GPUs. And we have actually talked about that in one of the First Principle videos. However, the traditional three-tier cloud-based network architecture do hit scaling limits and reliability challenges, after that point. If you think about a three-tier cloud network, the third tier does add cost and power to the cluster network. And, that makes one wonder, can we do better? Right, and save the cost and complexity, if you will, with two-tier networks.
The three-tier cloud actually scales well to that scale, no problem scaling up to 130K, but there are certain limitations, and as you pointed out, power efficiency, cost efficiency, and reliability of the network are those challenges, and we wanted to do better. In fact, our customers wanted us to do better, and we've met them where they'd like us to be, and we believe we have a new architecture that solves for those very problems, gives us the large scale we want, gives us the power and cost efficiency we want, and gives us the network reliability we want, and that's what we're here to talk about today.
Awesome. Well, so obviously this required us to, fundamentally rethink the network architecture. So David, tell us a little bit about, this key innovation of multiplanar network.
So multiplanar networks are multiple planes. The three-tier network that we built before was a single network connecting all the NICs that are in the network. The multiplanar network, we have individual planes that each connect to a single NIC. How does that work? Well, there's a little switch in the latest NICs that allows the computer to send stuff out to the NIC, and then the NIC spreads it out to 4 different switches. So the NIC itself connects to 4 different planes in our multiplanar network.
Got it. So essentially now the NIC itself is like a mini switch, and it's almost like we are using that as a bonus tier in our network, if you will. Is that how it works?
Yeah, so we have extra planes. We can add planes to get more bandwidth. We can add planes to get more reliability. And without this third tier, which cost quite a bit because it was as big as the other tiers, so we get a whole lot fewer switches.
All right, got it. So essentially, we use the NIC to, come up with broader but shallower, network, if you will, in order to connect more number of GPUs, but with less tiers, right? And that's essentially what saves power, and presumably it also saves cost because you're going to have less number of chips, or the switches, if you will, in the fabric, because we're going to use the NIC itself as one of the tiers of the network. So that's really awesome. So, but then it brings another question, though. If a NIC essentially, has to connect to a whole bunch of, switches or different, fabrics in this case, what essentially happens on the NIC? It's almost like the NIC is participating in the routing and the switching of the network itself, who actually does all this work? Is the NIC doing that work, or is the software above it doing the work? What happens there, Jack?
It's done in both places, and we're pursuing both in the NIC and in what I would call host-based libraries. And in the simplest form, NIC has new firmware where it does this spraying of traffic, if I could use that word, because some people may be familiar with packet spraying. So spraying of traffic across all the multiple planes. And then on the other end, receiving NIC coalesces all these sprayed flows into a single flow and present it as in-order chunk of data to the application. So NICs can do that, and host libraries can do that as well, and we're looking to do both.
Got it. So, but then, are you saying that perhaps in a single network connection or a queue pair, we actually take the packets and spread them across all the links?
Yeah. So in one form, it could be presented as a single queue pair to the application. Queue pair being an IB terminology, Rocky terminology, which is a flow from the application standpoint, and then underneath it, the NIC or some host software in the library spreads that QP across all the planes. That's definitely a valid form. Another form is you have the concept of maybe like a virtual QP and a bunch of physical QPs underneath it. So there's multiple ways of doing it, but the main idea, the key insight is to spread the traffic across all the planes, do the coalescing on the receive side, and then presenting it to application in order. Because remember, most RDMA libraries, RDMA applications expect in-order delivery of data. So from an application standpoint, everything is in-order delivery.
That makes sense. So, that does mean that, the NIC or perhaps the software above it has to know which links are up, which is generally, what NIC does anyway, so that's fine. But then it also needs to have some sense of, what may be a preferable path from a, congestion standpoint. And the NIC or the software does that?
Correct, you're right. So you touched on two really important points. One is the health of the NIC port breakout. As David described, a NIC is being broken out into multiple ports. The firmware on the NIC would be aware of which port is up or down, and if a port is down, it'll stop sending packets that way. So that's one. The other is if something happens downstream in the network, right? Let's say there's a link failure between switches within a plane. You now need to do something about it. There's two ways to handle. There's more than two ways to handle, but at least two. One is switches will detect those failures, and they would reroute packets using dynamic routing, load-based traffic distribution, load-based ECMP, or the host-based application or driver firmware in the NIC can do the same by doing some intelligent health checking. So there's more than one way of doing that, but in either case, the idea is to detect link failures and work.
Got it. Cool. Awesome. And then on the receive side, who's actually doing, you said if there are out-of-order packets, it's going to be reassembled in some fashion. What exactly, who does that? Is that the NIC that's doing it? Is the software that's doing it? Well, how does it work?
Yeah, and in most cases, it is the NIC doing it. As you may be familiar, there is a consortium called Ultra Ethernet Consortium, which is also pursuing something very similar, which is packet spraying and then in-order delivery to the application. And in case of UEC, there's effectively a bitmap is maintained, and then you make sure all the packets have arrived, and then you do a single completion to the application.
Got it. Cool. Awesome. So that way, the out-of-order packets are not stored in the NIC's memory, which is, really small generally. So we actually, put that in place into the RDMA buffers directly, but then we just delay the completion if there's the out-of-order packets, if you will, and that way, the application gets the completion, they are in out of order, right? Okay, got it. So, David, how does this all help with the reliability of the network?
So it helps the reliability because we have multiple paths. Multiple planes gives us multiple paths, and there's a much better chance, I hesitate to say always, but there's, practically speaking, always a path from one end to the other end. So the workload never gets interrupted. In the older days, we had one connection coming from the NIC to the switch. If that went down, there's no alternative. So now there's always an alternative path into the network.
And David is absolutely right. So one sort of axis of reliability we gain here is because there's not one network to fail. Now there are multiple planes, disjoint planes, as in the control plane of these fabrics, these planes is completely disjoint. As an example, if there's a BGP outage in one plane, it will not impact other planes. So you now get much higher reliability because a failure in a plane will never impact another plane. And you have the control on the host, on the NIC, to switch over to another plane. So it should give you much higher reliability.
That is absolutely fantastic. It's almost like, you have, 4 or 8 completely isolated network. Now, even before any of this, we have tons of redundancy within a network. So, multiple links fail, multiple switches fail. The network is, generally reliable. However, if there's a control failure of some form, that could potentially affect the entire network. And we've seen that happen in rare cases. But I think what I'm hearing is that these are 4 or 8 independent networks with completely independent controls. And really the only joining place for all these networks is on the NIC and the software. And as a result, the network itself is fundamentally isolated. It's almost like, in the software world, if you think about OCI, block store service, and object store service, we essentially have, redundancy within the service, but we also have, bulk hitting, if you will, so that there are independent sets of, clusters, and they don't, fail together because of full isolation. So it's essentially we're bringing in, similar architecture to the networking world, the physical networking world. Yeah, that's really great. So David, how does this multi-plane network architecture, benefit OCI's AI infrastructure?
So, like I said, it's reliable, and they get this reliability by having these, like you said, bulkheads between the different planes. And that means we can do operational work on a particular plane, if necessary, intrusive operational work that would affect traffic, because there's other planes going to keep the job alive with that traffic. And so that's good operations. If something breaks, the same thing applies. So we got good reliability. The other thing that we do with these planes is we keep it at 2 tiers. And to get it down to 2 tiers, we had to do a thing to increase what we call the radix of a switch. Now, it's a technical term, but that means how many devices a switch can connect to. On a switch, you have 64 ports in the front. It can connect to 64 things. Well, we can break out those ports and connect to many more devices. In this case, we're connecting on one switch to 256 other devices.
Got it. So essentially, you break them out. And that's essentially how you get a lot broader network, if you will, because the radix of the switch is much higher, effectively.
Exactly. There's a little bit of math involved. So on these fabrics, if you increase the radix, the size, number of NICs that you can connect is proportional to the square of the number of ports, the effective number of ports. So 256 squared is so much bigger than 64 squared.
So scale is one big gain by having larger radix, and closed networks scale at the exponent of the number of tiers. So we get much larger scale, which is a key property. The other is, as David said, much higher reliability, because we can fail planes, we can do maintenance in the planes without impacting. So these are really big wins. And another win is, as an example, if we were to go from a single large 3-tier network into multiplanar 2-tier network, and by the way, you can still have multiplanar 3-tier networks.
Yep.
And one day we may very well do that. You get even larger scale. But let's say you go from a single 3-tier Clo fabric to multiple 2-tier multiplanar fabrics. The other couple of other advantages you get, which are a side effect of this, is one is because you have fewer switches. Therefore, you have fewer links, fewer optics, you save power, and you save latency. Because you see, in a normal 3-tier Clo, you have an extra tier of latency between the second and the third tier. That doesn't exist here. So we have also lowered the latency of the network, and some workloads actually care about that.
Yeah, absolutely. AI workloads, care a lot about latency, particularly in specific conditions. And, I think what I'm hearing is, no matter what, there's going to be a NIC, and there's going to be, there's latency associated with the NIC. But now we're using that as a switch as well, a mini switch, if you will, and eliminating one of the external other tiers, the third tier of the network. So the latency comes down because, the depth of the network is smaller now, right? So that's really good. But, one thing that occurs to me is when you actually have, a 4-way or 8-way split. Let's say you take a 800 gig NIC and do a 4-way split or 8-way split. Now you have lots and lots of cables coming out of every NIC and every switch. And we already know that cabling complexity is one of the biggest challenges with any form of supercluster builds, because we want to build them out as quickly as possible. And there's a lot more cables to actually cable them up. Now, with this multiplanar array, it looks like you're going to have 4x or 8x more complexity. How do we actually deal with that?
Yeah, you're absolutely right. This does have a lot more fiber strands involved than it does with the traditional networks. So they talk about how many times you go back and forth to the moon with these strands of fiber that we've installed. There's also another complexity. It's if the switch is breaking out 4 ways and the host is breaking out 4 ways, this doesn't really work. So we had to come up with inventive cabling solutions to make the switches breakout and the NICs breakout actually connect to each other. We called this solution shuffle cables. And that shuffle cable also brings together a bunch of the fibers that are involved with this connection so that it actually will reduce how many cables have to be run, how many strands are run, and makes it simpler for the installers to manage.
Got it. So essentially we have, a consolidated cabling, if you will, that also shuffles, cables from one thing to another so that you kind of get the whole point of cabling is to actually make, each link go from one location to another, but you kind of get the shuffle, if you will, but without actually having to have 4 different individual strands of cable, because the cable, the consolidated cable itself will shuffle the links. So that's really good. That's a really good way to, reduce the complexity. Yeah. Well, so let's talk about optics. A huge part of the power consumption for networking is actually the optics. And there's a lot of, innovations going on in the optics world. So Jack, can you take us through, some of the innovations in that space?
Yeah, so as you said, these large AI ML workloads, they're very power hungry. GPUs consume a lot of power. And it's quite often that the scale of the fabric or scale of the cluster is really determined by the power available, right? So power is the precious commodity. So we want to do whatever possible to save wasting power. And our customers have given us very clear feedback, hey, the network is consuming a lot of power. It's not just us. For everyone, network is consuming a notable amount of power. So we want to do whatever possible to save power in the network so we could give that power to our customers to have more GPUs, to have larger clusters, and to run their workloads at a larger scale. So there is a new class of optics that allow us to do that. What we call traditional optics is what we refer to as fully retimed optics, FRO. And by fully retimed, we mean if you imagine 2 switches or a switch or a NIC connected to each other, there would be 2 DSPs on that optical link in between the switch and the NIC, or between the switch and a switch. And the purpose of the DSP in most data center optics, modern data center optics, is to implement modulation schemes, because these newer 400, 800 gig links require more complex modulation schemes. So they implement modulation schemes. They do all kinds of link stabilization, cleaning up of the signal. There's a lot of complex logic that runs on the DSP. But these are processors that consume power, and they need to be cooled. So there's a lot of power that's taken up by these DSPs. It turns out, over the last couple of generations of switches and NICs, the switch and the NIC chips, their SerDes, or their interface towards the optics, has gotten so much better that some of the DSP functionality could now be implemented on the switch and the NIC. And that's what we call linear optics. And there's 2 categories of them. There's linear pluggable, LPO optics, and there's linear receive, LRO optics. Linear pluggable optic eliminates both of the DSPs, and linear receive eliminates one of the DSPs on the link. And the end result is you save a little bit of latency, but you save a significant amount of power. And that all adds up. And since we consume less power, there's less power is dissipated. So the module, the optical module, runs less hot. Therefore, less cooling has to be done. Therefore, the fans in the switch and the host could run a little slower. And I'm sure you're aware, fans follow this other set of fan laws, whereas the speed of the fan grows, the amount of power you need to power the fan grows at a very high multi-order exponential. So by using LRO LPO optics, not only do we save power on the optic, we save a lot of power on the fans. And we can give all that power back to the customer.
That's fantastic. All right, well, thanks, Jag and David, for talking about how we design the multiplanar network. The innovations here are really astounding in terms of reliability, scalability, and efficiency. All three that matter a lot for our AI customers as well as other enterprise customers.
Yeah, we're building gigawatts of GPUs, and for that we need just super innovative networks, and we have more innovations in the wings. Watch this space.
Yeah, I agree. There's lots of things cooking. Hopefully we'll have more things to talk about in the future. And thank you, Pradeep.
Awesome. Thank you. All right, so let's summarize the key takeaways. Multiplanar network is a breakthrough network architecture that significantly increases scale, reliability, and security, particularly for AI infrastructure as well as for any other enterprise network architecture. Multiplanar network results in a lot more breakout cables coming out of switches and the NICs, and that generally will increase the cabling complexity. So we use shuffle cables to simplify the cabling complexity so we can actually deliver the superclusters much faster to our customers. And optics is a huge part of the cost and power consumption in our network, and linear pluggable optics is a key way by which we are significantly reducing the power consumption of our network. Thank you for watching.